In the first kinetics lesson, we discussed the collision theory and how different factors can affect the rate of the reaction. We looked at how temperature affects the rate of the reaction and used the Maxwell-Boltzmann distribution diagram in order to explain that factor. We looked at how the activation energy of a reaction can affect the rate, and we looked at potential energy diagrams in order to explain that. What we didn't look into with any great detail was how the concentrations of reactants will affect the rate of the reaction. We need to study this in more detail by presenting the rate law. The rate law of a reaction is going to give the relationship between the rate of the reaction and the concentrations of the reactants. We know that the rate is proportional to the concentration of the reactants in a reaction. So for example, in this reaction A plus B going to some products, we know that the rate is going to be proportional to the concentrations of A and B. We know that it's proportional, so if we want to change that into an equation, we need to introduce a constant. And the constant that we're going to use in our rate law is lowercase k. It's called the rate constant. So this equation that we have right now shows us that the rate is dependent on the concentration of the reactants. Now what you'll notice is that there are powers that the concentrations are raised to. And this is what we are going to be looking into in more detail. How much a particular substance affects the rate of the reaction and how it affects the rate of the reaction must be determined experimentally. And it's not dependent on the coefficient in the balanced chemical equation. And we must use experimental data in order to determine the powers of the concentrations in the rate law. So let's look at an example. This reaction here has this experimentally determined rate law. So the rate is equal to a rate constant times the concentration of H2SCO3 raised to the 1, I minus raised to the 3, H plus raised to the 2. You'll notice that the coefficients in the balanced chemical equation do not match the powers in the reaction. These powers are determined by experiment, and you'll see the experiments that are done in order to determine them. These numbers are called the order of the reactant. So this particular reaction is first order in H2SCO3. It is third order in I minus, and it is second order in H plus. The overall order of the reaction is the sum of all of the exponents. So in this case, the overall order of the reaction is 6. Now, the meaning of the exponents is going to become more clear as we move through the lesson. For now, we're going to look at the experimental data that's collected and how we can use it to determine the order of a particular reactant in a reaction. In order to determine the exponents in the rate law, what we need to do is we need to change the concentration of a particular reactant, and we need to monitor what happens to the rate. So for this particular reaction, if we want to study it, we've got one reactant. So an experiment that would be done to determine the rate law would be one where we change the concentration of the N2O5 and look at what happens to the rate. So this is the table in your notes, and you can see what happened to the rate. So in this case, we halved the concentration, and the rate was also halved. Okay, so we need to look at the relationship between the concentration and the rate. We know that the rate, in general, is equal to K times the concentration of N2O5 raised to some power. So what we're trying to determine with this data is what the exponent is. And in this case, if we halved the rate, okay, when the concentration was halved, we can see that in order for this expression to be true, the exponent needs to be equal to 1. The rate constant here is a constant. Okay, so we're looking at the connection between the concentration, the exponent, and the rate. So the rate law for this particular reaction is the rate is equal to the rate constant times the concentration of N2O5 to the 1. So for this particular reaction, it is first order in N2O5. Okay, let's look at another example here. In this example, we're looking at this reaction here. So NH4 plus NO2 minus goes to N2 plus 2H2O. The experimental data that we've collected is here. Now in this case, we're looking at a scenario where we've got two reactants. So we know that the rate is going to be equal to the rate constant times the concentration of NH4 plus raised to some power times the concentration of NO2 minus raised to some power. The exponents of the reactants each need to be determined experimentally and separately from one another. So in order to set up an experiment, what we need to do is we need to change the concentration of one reactant at a time and look at the impact on the rate of the reaction. So let's look at comparing trial 1 to trial 2. The concentration of the NH4 plus has been maintained. But during that time, what has happened is the concentration of the NO2 minus has been doubled. So by examining trial 1 to 2, we're going to be able to see what the exponent of NO2 minus is in the rate law by looking at what happened to the rate of the reaction. In this case, the rate of the reaction when we doubled the concentration of NO2 minus is also doubled. If you're not sure, what you can do is just divide, take the 2.7 times 10 to the negative 7 and divide by 1.35 times 10 to the negative 7, and you'll see that it's double. So the constants in this situation are the K and the NH4 plus. I haven't changed the concentration. So I know the change in the rate by doubling the rate has come from doubling the concentration. So we can take a moment and look at what that means for the exponent. In that case, the exponent needs to be equal to 1. Okay, so we know the exponent n is equal to 1. To look at the impact that the concentration of NH4 plus has on the rate, we need to compare a scenario where the concentration of NO2 is being held constant. So if we compare trial 2 to trial 3, you can see that the concentration of the NH4 plus has been doubled and the rate of the reaction is also doubled. As we saw from our previous example, when the rate is doubled with the doubling of the concentration, that means that the exponent must be 1. So for this particular rate law, both the exponents are equal to 1. So the formal rate law is NH4 plus times NO2 minus. Now, what we can also do is determine what the rate constant is. Okay, so if we look back to here, If we want to determine what the rate constant is, we've got the rate law, we know what the exponents are, and we've got an equation. So if we want to figure out what the constant K is for this particular reaction, what we need to do is take one of our sets of data. So in this case, if we take our data from trial 1, and we need to sub that into the rate law. So we know the rate, we know the concentration of NH4+, we know the concentration of NO2-. We can simply rearrange this equation in order to solve for K, the rate constant. And the rate constant here is 2.7 times 10 to the negative 4. And I'll talk in a moment about how to determine the units for this. So if we want to know the units for the rate constant, and it's important to determine these because they do give us information about the reaction, to look at what we have. So rate is equal to the rate constant times the concentration of various reactants and products. The units for rate are mole per liter per second. So mole per liter second. The units for concentration are mole per liter. So in this case, in the example that we had, if both of the concentrations are first order in the rate law, this is going to be mole per liter, this is going to be mole per liter. So when we look at this, if we want to rearrange to find the units for the rate constant, we've got mole per liter per second, and we're going to bring the liter squared over and the mole squared over. Okay, so the units for K are going to be liter per mole second. Now this is for a second order reaction. Okay, if I change this, so say it becomes a third order reaction and this is squared, this is going to be squared. So what's going to happen is this is going to be cubed and this is going to be cubed, and I'm going to be left with squared and squared. If this was a fourth order reaction, so a 2 and a 2 or a 1 and a 3, then what's going to happen is this is going to be a 4, so I'm going to have a 3 and a 2. Okay, so if you look, if you've got a first order, second order, third order, the units, you could work it out for each one. The units for a first order reaction are 1 over S. For a second order reaction, our liters per mole second. For a third order reaction, our liters squared per mole second. For a fourth order reaction, our liters cubed mole cubed per second. Okay, so if you can see the pattern here, in general, the units for the rate constant are liters to the n-1 over mole to the n-1 per second, where n is equal to the overall order of the reaction. Now, this is important because it's expected that if you're given the units of the rate constant for a particular reaction, you should be able to state the order of the reaction. That's why we need to review this. So what that also means is that when you're given data from a reaction and you're asked to find the rate constant, you need to include the units for the rate constant. You can either use the general formula for the units, or you can set it up and just solve algebraically to figure out what the units are.